So let's see, our next keynote speaker, Tirthankar, is Vice President for Data and In-Memory Technologies at Oracle. He is also responsible for the Oracle Database Engine, which includes database in-memory, data and indexes, space management, transactions, and the database file system, as well as the Oracle x10 in-memory database and Oracle NoSQL DB. Tirthankar has 22 years of experience in the database industry and has worked extensively in a variety of areas, including manageability, performance, scalability, high availability, caching, distributed concurrency control, in-memory data management, NoSQL architectures, and more. He has 27 issued and several pending patents in these areas. He has a B.Tech in computer science from the Indian Institute of Technology and an MS in electrical engineering from Stanford. Please welcome Tirthankar to the stage.
All right, hello everyone. Thank you for the introduction. My name is Tirthankar. I'm the Senior Vice President for the Data and In-Memory Technologies organization in the Oracle database. I should stand here, I guess, right? Can you guys all hear me? All right. Okay, so, trouble is I can't see the slides from here, but I'll try to wing it. Okay, so I thought the best way to wake everybody up is to give everybody a history lesson, because what's more interesting than history? So I'm going to talk about the history of data management basically in one slide, and that history is divided into 4 broad eras. And the good thing is each era was accompanied by a corresponding era in a different type of enterprise, which is the Starship enterprise. So the first era was the mainframe era. And to me, the face of the mainframe era, with apologies to the speaker from IBM, Maithili, is Captain James T. Kirk of Starship Enterprise. He was the defining face of that time period of the enterprise. There you are, thank you. I like it, right? Good, good. So then he gave, he passed the torch on to his successor to usher in the client-server era, and that was Captain Jean-Luc Picard. And Jean-Luc Picard, again, was the face of the client-server era, but then he, too, decided to pass on the responsibility of continuing the Star Trek tradition to Captain Benjamin Sisko, who then ushered in the Internet era. But the Internet era was really defined by actually my favorite Star Trek captain, which is Captain Catherine Janeway of the Voyager, right? She was the face of the Internet era. And then she too transitioned on to Captain Jonathan Archer, who brought about the cloud era, which we're in the middle of. It's the era of today. And I haven't seen Star Trek Discovery myself, but Captain Lorca is supposed to be the captain now. I don't know if anyone's watched Discovery. I've seen every other Star Trek series except for this one, but that's on my to-do list of things to do. So these are the voyages of the modern enterprise, which is constantly seeking out strange new algorithms, data models, weird new workloads. And it is true that no matter what databases do today, the modern enterprise wants to go where no database has ever gone before. This is a fact. And this is what's driven innovation in our industry to such a great, it's a great time to be in data management because there's so much richness and so much sophistication in the requirements of today. So let's quickly talk about these 4 eras, hopefully without putting everyone to sleep. In a way, the mainframe era is the most fascinating to me. It was the era defined by the war of paradigms between imperative programming and declarative programming. There were systems like Codicil, IMS, ISAMs, which really had imperative constructs where you told the database how to process actions, how to run queries. And the upstart rebel then, believe it or not, was the relational database. Everyone thought the relational database guys were crazy because you would just tell the relational database what you wanted to know, the question, and it would figure out how to derive that answer. At that time, it wasn't clear which one would prevail. In fact, in the mainframe era, IMS and Codicil were by far ahead of the relational database in market share. It wasn't until the client-server era that the relational database really pulled ahead. And this is something people lose sight of. The reason this happened was really because of developer productivity. The relational database gave you standard APIs and languages, so an expert on Oracle could easily become an expert on DB2 and vice versa. You had the database provide you with consistency, with atomicity, with integrity, so developers could really focus on their core mission, which was developing application logic, because the database simplified so much of the other tasks the developer would otherwise have to do. So it's a very important thing to recall that the reason the relational database took off was because it empowered developers. Now, the internet era was when the database really came of age because the internet brought about massive requirements. Anyone recall these quotes? The internet changes everything. The network is the computer. Anyone recall this? A few people, okay, yes, it was said. These were actually said by these gentlemen. So volume increased, scalability increased, requirements increased. There was never a downtime in the internet, so availability was 24/7. Variety increased. Suddenly there were lots of new data models. And at that time, for a short period, single-purpose databases like text databases, XML databases, they did come into existence. But they went away once the mainstream databases adopted these technologies. And of course, security became a very big deal because the internet has a much bigger surface area than the enterprise. Okay, so if I ever become famous, you can quote me for this, as having said this, that the cloud changed everything. It's true, but I don't think anyone said that explicitly. So I'd like to take credit for it 10 years from today, if I'm famous, if I'm well known by then. It changes everything in the enterprise landscape, development, deployment, especially development. The cloud really is the golden age for developers. Developers become essentially users themselves, planet-scale users. And it really democratizes and empowers development, makes it very easy for everyone to develop applications against databases. And the paradigm of today is microservices. This is a very important transformation in application design, where each microservice encapsulates specific functionality. They communicate via events. They're lightweight, they're agile, and they're highly available. If a microservice fails, they don't take the whole application down. They are basically fault isolated. So this is the great new paradigm for developing applications. And it's with this backdrop that we now see, again, a revival of single-purpose databases. This really began because of the web giants, Google, Facebook. They all discovered that their specific needs are better met by specific custom-built engines, like Bigtable, Cassandra, et cetera. There's lots more now, lots of NoSQL products that all serve different use cases, different data models, different APIs. And they all do provide performance, functionality, scalability, availability. They all have certain trade-offs. But this is very much, a trend today, where there's a lot of single-purpose databases that do specific things for applications. At the same time, the relational database world hasn't been sitting still, and Oracle has certainly continued to evolve. Oracle is now what we call a converged database, where it doesn't just run relational query processing. It runs a lot more. It's evolved well beyond what one would think of as a classical relational database. Oracle has support for documents, and especially with JSON, including text and XML. It has a lot of support for AI and machine learning, spatial and graph, as well as many other workload types, IoT, time series, even file systems. So this is the current situation. We have an abundance of single-purpose database engines. We have a very powerful converged database platform. And so the question is, where do we go next? Which is the present-day data architect's dilemma. If somebody were to set up an enterprise from scratch and define their data architecture from day one, how would they go about it? Okay. So basically two choices. You can either go with disjoint database engines or a converged engine. And let's discuss what we think the trade-offs are with these choices. Right? So first of all, the single-purpose database engine approach, it's reasonable for microservices if you really want function independence of the microservices, because you can have your graph service running on a graph database and your documents service and document database, which each of these are purpose-built, highly optimized, and many people do this. It's a reasonable way to go. These databases remain independent, and they're also fault isolated. If one database fails, it doesn't affect the other ones. So your microservice architecture remains highly available. So superficially, this seems like a good fit for the modern world. However, it's important to note that this is not essential. I've heard multiple times that I need these engines to run my different use cases. This is actually not true. You don't need separate databases to run different workload categories. What you do need is you need separate algorithms and separate data models. That is required. You can't shoehorn everything into the relational model. That is valid. However, having separate engines is not a requirement. You can achieve this separation of function both with multiple single-purpose databases and a converged database. The other issue with these single-purpose databases is they're really single-purpose. They're designed to do what they do. They're well designed for their specific use cases. But they do lack many of the properties that made the relational database successful in terms of empowering developers. Things like data integrity, sophisticated indexing, full-feature transactions. Now, developers are smart, and they do work around these shortcomings. They'll build a lot of application-level logic to implement these requirements. But this is necessary since these engines don't always have these properties as native features. The other issue is that each of these engines is distinct, that a MongoDB expert will not be an expert in Neo4j. They're totally different databases, different models, different paradigms, different dialects. So the skills aren't interchangeable. If you build an architecture based on multiple single-purpose databases, it creates infrastructural issues in the long run. You have to worry about keeping data consistent, keeping compatibility in mind as you upgrade different components. Each product needs a separate set of security patches, separate upgrade cycles. Analytics across multiple disjoint engines requires really integration and federation. It's very complicated. And consistent backups is tricky. Backing up 7 different engines consistently at the same point in time is hard. One other thing that people overlook is when you have your application running against multiple databases, there's a huge amount of state that the application has to manage. The application must manage atomicity. I just recently booked a vacation on Expedia where I wanted the vacation to go through only if I could get the hotel, car, and airfare together. Now, if these things ran on separate databases, then keeping that atomic would be the application's problem and run compensation in the application. So there's additional challenges in maintaining the integrity of workflows when my participants are multiple databases, and handling failures and managing security uniformly. All of these things become more complicated. So this is a slide from a real customer. It's a very large web company. It's from their architectural presentation where they talk about multiple engines that they have for running their infrastructure. I call it die by DYI. Now, it works if you can hire the brightest MIT, Stanford computer science PhDs and keep your workforce full of incredibly smart talent. You can get it to work. It's not impossible, and they've clearly done it. It's possible to get your system to work this way. It does have a lot of trade-offs. Now, they talked about the advantages. I saw a lot of issues. I saw the fact that multiple data stores, no less than 7 or 8, if I'm counting correctly. It suffers from what we call copy contagion, multiple copies of data to do analytics. Security is tricky. You're as secure as your weakest link. You're not as secure as your strongest database. You're as secure as your weakest database, because that's what's going to get hacked. Maintaining consistency as data moves around is, again, the application's problem. And as I said, if you can hire the best, smartest, brightest, the entire graduating PhD class of MIT, yes, this would work. But it's not for everyone. It's really not meant as the default approach for your enterprise. So let's talk about converged data. You can see where I'm going, obviously. So you'll say, okay, so you're saying a converged database is the right solution. Well, the whole point was that you guys didn't scale well enough to achieve cloud scale. So can you really scale to meet my requirements? And the answer is yes, it is possible, certainly possible, for a converged relational database to scale to cloud volumes. And there's again a myth that the relational database is just intrinsically too complex to scale. It is more difficult to scale relational database than a key value store. I mean, there's a lot more functionality, but it is possible. And I've been Oracle for a very long time, actually 24 years this year. And every year of Oracle database development I was involved in involved scalability initiatives, beginning with Oracle Parallel Server. Anyone recall Parallel Server? Anyone here? Oracle old time? Oh yeah, well, good, at least one person. Which became RAC. So we've done a number of things like RAC, Exadata, that have made Oracle more and more scalable over generations. And each release has tackled scalability as a fundamental goal for the release. And I'm not going to go through all of this because I could spend the entire day talking about Oracle scalability features, but the important thing to note is scalability in Oracle is achieved not just in software, but also in the platform, which we call Exadata. There are certain things you can't do in the software alone. You have to do it in the networking, storage offload. So these things combined give us a unique position in the scalability continuum. And as you can see, this is just 20 years. But in the last 20 years, every release of both Oracle database and Exadata have tackled really tricky scalability issues. So I'll talk about 3 features quickly in the interest of time that really empowered the cloud era. And since this is the In-Memory Summit, I'd like to talk about database in-memory, which is our technology for converged analytics and transactions. It is the industry-first dual format architecture where, in addition to the row format, we create an in-memory column format for high-speed analytics. So the same data can be both in the row format for OLTP and in the column format for analytics at the same time, without any data movement. This allows real-time analytics against current data without the need to do any cross-database data movement or integration. The big magic, back here. So yeah, this was released in 2014, I believe, and 2017, which was the first and the last Forrester wave on in-memory computing. Forrester gave us the highest position in both current offering and our future direction. So it's a good testament to the technology. The magic behind in-memory, this is probably old hat to many of you, I just go through this very quickly. It's really this science of vector processing. Because you have data arranged in columns, it is possible to scan the columns as contiguous chunks of memory, feed the values into SIMD vector registers, and process them with one instruction. So for instance, searching for all the states that match California, you can do multiple matches using a single SIMD vector register instruction. And this leads to billions of rows per second scan speeds. This is columnar database basics. This is why the column stores are so fast for analytics. They not only help analytics, however, they can also accelerate converged workloads that include both analytics and transactions. Traditional databases have a number of indexes, which are basically present for analytic purposes, which slow down transactions because the indexes must be maintained. You can replace them with the column store. And the benefit there is it's like having an index on every column. It's in memory only, so maintaining them is fast. Maintaining the column store is very fast. And since you no longer have to worry about analytic indexes, the database size also decreases. And this is just simple benchmark we ran internally. We constantly test our product internally. We just tested this, showing that if you have an in-memory column store, yes, as you can see, on the right, we have the analytic queries that significantly speed up by close to 100x in one case and 10x in a different case. But if you notice the first 3 bars, we also get faster DML execution because those DMLs now no longer have to maintain indexes. So inserts, deletes, and updates all become faster with the column store. So it's a very important technology for running converged workloads. Another important feature of Oracle database in the cloud era was multi-tenant. It basically lets you manage many databases as one. It basically takes a physical database or a container database that can then host multiple virtual or tenant databases. So this is totally application transparent, allows very efficient resource sharing between the tenants, and simplifies management because you now have to upgrade and patch only one physical database, but you get isolation between tenants and as well as efficient resource sharing. So it's a very important cloud enabler. And finally, the third feature I want to talk about, which really makes Oracle database reach hyperscale, is sharding. There is a point beyond which a single database just isn't sufficient. You run into edge cases with very large databases and very large numbers of users. So sharding is a technique to divide a single logical database into multiple disjoint physical databases. And Oracle supports up to 1,000 shards natively with native SQL that can be sent to the specific shard of interest. So you can have, for instance, shards that represent different geographies and route queries to the specific shard based on your shard key, which in this case would be region ID. Shards can be organized online, reorganized online, and Oracle database scales linearly with shards in terms of both throughput and user population. And again, sharding is another way to manage the database more effectively. It is a lot easier to manage a sharded database as opposed to 100 completely different disjoint databases. So there's a lot of evidence in the real world that Oracle does provide hyperscale. Again, I'll go through this very quickly. SK Telecom is a giant telecom in Korea, processes 65 billion transactions per day on the database. The Department of Homeland Security processes over 30 billion operations per day on a very large database. And the New York Stock Exchange, another real-world hyperscale use case, the world's largest stock exchange, they process about 1 billion operations per day on the same database. So again, Oracle database is used in hyperscale environments today. So now that I've said that Oracle database with its converged functionality can reach hyperscale, what about the functionality itself? Is it as good as a single-purpose database? And the answer is yes, it can be. It's not just us that say it. Gartner did an evaluation of the technology vendors and rated Oracle as #1. This is in the report last year in 2018. That Oracle ranked first in every single use case for what they call operational databases. The one on the right talks about convergence of operational databases and analytics. There's basically 4 use cases: traditional transactions, converged analytics, event processing or data in motion, and what they call distributed variable data. So every single use case, Oracle ranked #1. And more recently, Forrester announced in this year's wave, they now call it the translytical wave, where they basically evaluate vendors in their support for multi-model converged workloads. Again, Oracle came out ahead of everyone else with the strongest support for translytical operations. And a lot of this was due to the fact that we have this dual format in-memory technology, as well as support for multiple data models within the database engine. So a nice testament from the analysts. A little bit about JSON and Oracle. So Oracle's had native JSON support since database version 12c, which we have continuously enhanced since then. It's a very simple technology to use because you can simply apply the SQL everyone knows to running JSON queries. SQL can navigate JSON paths. The syntax is intuitive. You can just navigate JSON documents using the JSON dot notation. And it supports full-featured indexing of JSON using functional indexes. And if you want, you can also use in-memory columnar processing to really accelerate JSON processing. And this was a little test we ran against a document database specialist. It's a variation of the YCSB benchmark, known as YCSB JSON. This was developed by Couchbase. So we used this workload to try a document specialist that I won't name, and found that Oracle database actually performs extremely well compared to a database that does nothing else but run on JSON data. So it's a nice testament that you can build algorithms specifically for a certain use case within a converged database without trade-offs. Now, again, there's lots more. Oracle has native machine learning built in, a wide variety of machine learning models. Again, you can train your model and infer against the model all within the database without having the data ever have to move out. So it simplifies your architecture significantly. The same thing for spatial and graph. We have rich support spatial data types and graph data types in the Oracle database. You can run basically SQL, PL/SQL, as well as PGQL for navigating graph data. So a lot of richness and sophistication for spatial and graph. Now, one unique benefit of a converged database that you can't get from separate databases is synergy, which is what happens when the sum of the parts exceeds the individual parts. The combined benefit is bigger than the sum. Sorry, I didn't say it right. The combined benefit exceeds the sum of the benefits. Because when I have multiple models in the same engine, I can do cross-model processing. I can do relational processing on graph data. I can do machine learning against document data. I can do document processing on relational data. These are the things you can't do when I have data living inside different data repositories. So what ends up happening with a converged architecture is you end up with what we call convergent microservices. Instead of being divergent across different engines, these run against the same data in the same database in a convergent fashion. And it makes life simpler. You can really have a lot less state in the application and simplify applications. So again, empowering developers. You can push application state into the database. You can even persist events in the database. We have Oracle persistent event queues that make it easy to run events inside the database. And that database can manage atomicity, recovery, security, et cetera. So life becomes simpler with this architecture. Now, one thing is people will say, well, the whole reason for multiple single purpose was because I didn't want to put everything in one physical database. Now, this is another myth I'd like to dispel, that the converged architecture requires everything to be in one physical database. It does not. It's perfectly valid sometimes. It's a matter of policy to separate workloads because of isolation reasons, compliance reasons, or whatever. Sometimes although you don't have to, you may want to run your OLTP and analytics separately because maybe your analytics runs across multiple databases. You can still do that. But having a homogeneous database type makes it much simpler. So you can certainly have a separate analytics database which you maintain through a replication transport like Golden Gate. With multi-tenant, you get enormous flexibility. You can have microservices share a single tenant database, use separate tenant databases, or use separate containers altogether. So you have full choice and full freedom. There is no reason to believe you still have to put everything into one physical database. You can use separate databases. But having the same type of converged database just makes life easier. So I know I'm the last thing between you and the break, so I won't take too much more time. I do want to leave you with one thought, though. Think about what would happen if you took this converged database architecture and you enhanced it with machine learning so that you as a developer or user didn't have to do anything to manage that database. And this is where autonomous database comes in. This is Oracle's latest offering on the cloud as a cloud service. The autonomous database is self-driving. It runs basically itself. There's nothing for the user to do to keep it going. It's constantly self-administered. It's self-securing. It patches itself so that there's no need to worry about missing security patches. Encrypts everything by default, provides full data protection, even from administrators. And it is self-repairing. It recovers automatically from failures. We provide very high uptime guarantees. And compute can scale elastically as the workload needs. So there's no need to provision what you need for the worst case upfront. As your demands change, you can change your allocation based on the workload's needs. And this is all because there's machine learning throughout the stack. So machine learning helps in automatically detecting sick or failed servers or networks or switches running on the Exadata framework. A lot of work has been done into automating failure issues. So if you have database hangs or anomalies, we detect those. If there is a bug that you've hit, we will either match it to an existing issue and apply that patch automatically, or file a new service request saying, hey, there's a new issue that hasn't been identified before. And there's a lot of smarts in constantly optimizing the workload based on optimizer statistics, evaluating the workload for which indexes make sense. So it takes away a lot of the guesswork of running a large database at scale. So again, this to me is the ultimate converged platform because so much is done behind the scenes for you so that the developers can really keep focusing on development. So to conclude, actually not to conclude, sorry, I'm not done yet. A lot of customers, again, I don't want to go through all this in too much detail, but as you can see, they have all claimed high performance as well as cost reduction. So it's been a very well adopted, very successful product. And now to really conclude, I'd like to summarize with what I think is a good analogy. How many of you here today are carrying a real camera? Like not the people filming this presentation, but who's carrying a proper SLR camera, a real honest-to-goodness camera that does nothing else but take photos? Nobody? Anybody here with a GPS device, a TomTom? Anybody here with a Palm, PDA? Anybody here with a phone that does nothing but make phone calls? Nothing else, just make phone calls. Anybody? There is one person? Oh, wow, okay. I'd like to see it. All right, so who has a calculator here? Anyone in this room with a calculator? Okay, so there you are, no one. At one time, these were very common devices to carry. People had all of these things. What happened was they sort of collapsed down into one device. The smartphone replaced all of these devices. If I were to replicate the functionality of my smartphone, I would carry, I don't know how much, I would need a backpack to carry all the devices. I still have a camera at home. I haven't used it in years because my iPhone's camera is good enough for most cases. But again, it's not just the combination that simplifies my life, it's also synergy. If I get an email with a calendar invite in it, my calendar automatically updates. There's little things like that. If I have an appointment, my Maps application tells me how long it'll take for me to get there. So again, this is the synergy you get by having all these functions built into one device. And it's very similar in the data management world that a converged database essentially gives you a much simpler enterprise architecture and really lets developers focus again on their core mission, which is developing the application. I think that was my pitch for today. Thank you very much. Okay.